Though octet rule is generally applicable for the s-block and p-block elements, other rules also exist. For example, the duet rule or duplet rule applies to hydrogen, helium, and lithium. The noble gas helium has 2 electrons in its outer K shell. Since the K shell can only have at most 2 electrons, the valence shell of helium is a closed shell, so that helium is stable. Hydrogen only needs 1 additional electron to attain this stable configuration, while lithium needs to lose 1. Heavier elements, such as boron, that violate the octet rule due to too few valence electrons form electron-deficient species. For example, borane and boron trifluoride would require a minimum of 4 bonds with 8 electrons to complete the octet of boron, but they can only have 6 valence electrons in 3 bonds. All boranes are non-classically bonded compounds, that is, there are not enough electrons to form 2 center 2 electron bonds between all pairs of adjacent atoms in the molecule. For example, in diborane, 4 hydrogen atoms are terminal, while the other 2 bridge between the boron centers. The bonds between boron and the terminal hydrogen atoms are conventional covalent bonds. Each boron has 1 valence electron remaining for additional bonding. The bridging hydrogen atoms provide 1 electron each. The B2H2 ring is held together by 4 electrons forming 2-3 center 2 electron bonds. This type of bond is sometimes called a banana bond. Electron-deficient molecules often react so as to complete their octet. For example, when diborane is treated with lithium hydride and diethyl ether, lithium borohydride is formed, in which the boron atom becomes octet. Stable odd electron molecules are commonly considered as violating the octet rule. They cannot obtain octet configurations by means of 2 electron bonds. For example, nitrogen dioxide has 17 valence electrons. None of the resonance contributors has octet on all the atoms. Odd electron molecules can only obtain octet configurations by means of 3 electron bonds. For example, nitrogen dioxide must have a double bond, a single bond and a 3 electron bond to complete octet for all atoms. The molecular exists as a resonance hybrid of the 2 contributors. The bond length is 120 pm. This bond length is consistent with a bond order of 1.75. Though 3 electron bonds can be used to obtain octet configurations, molecular orbital theory can predict the stabilities and bond orders of such kind of molecules in a straightforward manner. Main group elements in the 3rd and later period can form hypervalent molecules, in which the central main group atom apparently bearing more than 8 electrons in their valence shells. For example, in phosphorus pentafluoride, if it is supposed that there are 5 true covalent bonds in which 5 distinct electron pairs are shared, then the phosphorus would be surrounded by 10 valence electrons, in violation of the octet rule. Sulfur hexafluoride, chlorine trifluoride, chloride ion, and triodide ion are other examples of hypervalent species. The debate over the nature of hypervalent molecules goes back to the 1920s. Lewis maintained the importance of the 2-center 2-electron bond in describing hypervalence. Pauling proposed that period 3 atoms can form bonds using s, p, and d orbitals. Thus, the valence shell or the octet is expanded. To form 5 bonds in phosphorus pentafluoride, 1,3s, 3,3p, and 1,3d orbitals combine to form 5 sp3d hybrid orbitals, which each share an electron pair with a fluorine atom for a total of 10 shared electrons, 2 more than the octet rule predicts. Similarly, to form 6 bonds in sulfur hexafluoride, 6 sp3d2 hybrid orbitals from 1,3s, 3,3p, and 2,3d orbitals form 6 bonds with 12 shared electrons. Langmuir, on the other hand, upheld the dominance of the octet rule and preferred the use of ionic bonds to account for hypervalence without violating the rule. For hypervalent compounds in which the ligands are more electronegative than the central atom, resonance structures can be drawn with no more than 4 covalent bonds and completed with ionic bonds. For example, in phosphorus pentafluoride, 5 resonance structures can be generated, each with 4 covalent bonds and 1 ionic bond, thus satisfying the octet rule for all the atoms. The resonance hybrid has 1 positive charge on the phosphorus atom and -1/5 charge on each fluorine atom. The validity of the octet rule for hypervalent molecules is further supported by molecular orbital calculations, which show that the contribution of d orbitals is small, and an occupied orbital is localized on the 5 fluorine atoms, leading to negatively charged fluorine. Nevertheless, for historical reasons, structures implying more than 8 valence electrons in main group elements in the third and later period are still common. This practice allows structures to be shown without using many formal charges or using partial bonds and is recommended by the IUPAC as a convenient formalism. On the other hand, showing more than 8 valence electrons in main group elements in the second period is considered an error. For example, ozone has 2 correct resonance structures, each with 1 single bond and 1 double bond, thus satisfying the octet rule for all the atoms. The resonance hybrid has non-zero formal charges and partial bonds. On the other hand, though sulfur dioxide has the same valence electron structure as ozone, the recommended Lewis structure has 2 double bonds, thus violating the octet rule for sulfur. This structure is preferred because it does not have non-zero formal charge or partial bond. The 18-electron rule is a chemical rule of thumb used primarily for predicting and rationalizing structures of stable transition metal complexes. The rule is because the valence shell of a transition metal consists of 5 d orbitals, 1 s orbital, and 3 p orbitals. These 9 orbitals can collectively accommodate 18 electrons. When a transition metal has 18 valence electrons, it has achieved the same electron configuration as the noble gas in the period, leading to the stability of the complex. For example, cobalt and nickel have 9 and 10 valence electrons, respectively. When carbon monoxide combines with a transition metal, it donates a lone pair to form a coordinate covalent bond. In coordination complexes, the carbon monoxide ligand is called carbonyl. Thus, nickel in nickel tetracarbonyl has 10 plus 4 times 2 is equal to 18 valence electrons, so nickel tetracarbonyl is a stable coordination complex. In contrast, cobalt in cobalt tetracarbonyl has 9 plus 4 times 2 is equal to 17 valence electrons, so cobalt tetracarbonyl is unstable. If the cobalt tetracarbonyl accepts an electron, cobalt will have 18 valence electrons. Thus, the cobalt tetracarbonyl anion is stable. On the other hand, in dicobalt octacarbonyl, 2 cobalt atoms form a single bond to share a pair of electrons. Thus, each cobalt atom has 18 valence electrons, so the dicobalt octacarbonyl is stable.